Have you ever bought an electronic device that was malfunctioning or not working right out of the box? That's a symptom of poor quality control, and it's all too common in budget 3D printers. It seems like every other printer that I get in for review or testing doesn't work straight out of the box, which is kind of shocking to me because I think these companies are sending me these products to do a review on, but if it doesn't work, what am I supposed to tell people? Usually I rag on the printers that don't work very well right out the box. My Ender 3S1 Plus is a perfect example of this. Some companies are better than others, but it seems like there's stories of pretty much every major 3D printer company producing kind of shit products that don't work, and that's something that I'd really like to see addressed. When a company produces low quality or malfunctioning products, I think it's disrespectful because it's wasting people's time, money, and resources, and who knows if they're going to honor their warranty and fix it and send you a printer that actually works after you've paid them good money for it. All of this can be resolved in the factory if they'd properly test their machines before shipping them out. And the factory is the ideal place to find faults because you've got everyone there that knows how to fix the machines, so they can go ahead and rework it instead of shipping it out to you and having you figure out how to fix it. I'd like to think that the free market would take care of this, and once a company has sold enough malfunctioning printers, reality, that people would stop buying them and move on to someone who produces higher quality goods. But as we all know, that's not really the case. People continue to buy these crap printers, and they have problems, and they end up having to fix them themselves. I'm not going to participate in that kind of nonsense. I'm going to make sure that every product that I ship out is tested, and I make sure that it works, so that my customers get the best experience. Now, if we get back to the development and testing of this board, I think unit testing and functional testing is kind of the fun part of doing engineering testing. Once you get into production, you kind of need to change gears a little bit. When you're working on a one-off prototype, you're doing tests to make sure that your design is sound and make sure that it works as intended. But when you get into production, your mindset changes from how do I make sure that this thing is working to how do I make sure this thing is working in 10 seconds because I'm going to be making a lot of these and I don't want to spend the rest of my life testing it. That's kind of the life you live in production testing. So let's get into that now. To help with quality control, I've constructed my lovely assistant here, Mr. Clicky. I have a professional background in design and test engineering, so you'll have to excuse that this thing is extremely over-engineered. I want to start with a philosophical question. Why do we test? I mean, wouldn't it be good enough if I could just make these things correctly the first time and then ship them out and everything will be fine? Well, the truth is, in manufacturing, things don't always work out the way that you think they will. You might put things together wrong, you might get bad parts in, or you might just have an inexperienced workforce that doesn't know how to put things together correctly. So you just have to check and make sure that things were done right as they learn and get better at the process. For this breakout board, I really want to make sure that I build these things right, because if you plug things in and there's unintentional shorts, it could immediately fry your printer, which is an outcome that I wouldn't want for anyone that's buying a board from me. I put together a little table of approximate fault rates for people that are building a circuit like this. So if you're an inexperienced assembler and you don't know how to put this kind of thing together, there's probably about a 50-50 chance you're going to create an unintentional short that could damage your printer on power up. So if I made 100 of these boards, 50 of them would be faulty goods, and that's not very good at all. If you look at my experience with Creality printers, about a third of them don't work right out the box. So that's a 33% fault rate. That's slightly better than an inexperienced assembler. If you step up to an intermediate assembler, someone with about my level of skill with putting electronics together, I'd say about 1 in 20 electronic boards are going to get damaged, or 5 out of every 100 boards that are built. Now you could say, Nathan, why don't you just get better at doing your job and put these things together more accurately? Well, you can, but there tends to be kind of an upper limit to how good you can get at putting things together. And even a very experienced assembler with years of experience might mess up maybe 1% of the boards that they're working on. So out of 100 built, one of them will have one tiny little error that might cause a short or might damage someone's printer. So if you want to achieve a higher pass rate, you're going to need to do something more to make sure that you're getting that level of quality that you need. If you upgrade to an automated assembly procedure, then you could get as low as a 1 in 1,000 fault rate. So if you built 100 of these, it's pretty likely that all of them are going to be perfectly good and working. However, there's a lot of overhead involved with setting up automated assembly, and if set up incorrectly, automated assembly can have a 100 out of a 100 fault rate. So say you programmed the machine and it's messing up every single one the exact same way, and messing up every board that you produce, well, that's not very good either. So even with automated assembly, you still want to have some kind of safeguard in place to make sure that you're producing a quality output. And that's where automated testing like this comes into play. Now you can do manual testing, but the problem with manual testing is just like manual assembly, there's room for error. So I might put my test probes on the wrong points, or I might skip a step and end up not catching an error. Automated testing like this is definitely the way to go if you want to ensure the highest levels of quality. So the way this machine works is when I finish a board, if there's no shorts, these lights should light up in sequence one at a time and have no duplicate lights. If there was shorts, then additional lights would be turning on as it's going through this process. So if I want to simulate a short, I can jam this screwdriver in here, and that's going to create unintentional electrical connections. So now you can see, as it's stepping through the different pin groups, when it gets over here, it's lighting two of these pins up at the same time. So right here, those two pins are lighting up together, and that's telling me that there's a short between those two pins. And this will work for any other pair of pin groups. I could manually probe each combination of wires looking for shorts, but there's 105 unique combinations of short pairs. This would take hours to test every board, and it'd be extremely tedious. On top of that, this type of manual testing is prone to error, so bad units would inevitably slip through the cracks despite my best efforts. So let's say I have a short between these two leads, which is a common fault that you might have if you're soldering these together and you have a blob connecting those two pins. You can see these two lit up, and that's indicating that I have a short along these two pins that are for the thermistor. Now if you have a bunch of shorts, let's say you have a big blob of solder connecting a bunch of these on the bottom here. We have a bunch of these lighting up, and when it gets to these three pins, you can see it lights up the group of them. There's some other ways that I could do this too that'll make it easier to spot shorts. So if I solder all of these ends together, I can get different behavior. If there's any shorts detected, all the lights will turn on, which will really be super flashy, and that'll be more helpful when I'm to the point where I'm not making many faults. But I kind of like the way it is right now because it pinpoints exactly where I should be looking when I see a short. Now if I have multiple shorts, let me just jam a bunch of screwdrivers in here. You can see I have double lights flashing here and double lights flashing there. If we wanted to take this one step further, I could program the Arduino to read these light bulbs and output that information to a computer program. And that computer program would understand that, hey, if these two pins are shorted, then I need to inspect this specific part of the board. This type of automated test report generation isn't really necessary on this device because it's just going to be me building and testing these. But you can imagine if you were part of a large manufacturing organization like Ford or Apple or Intel, then you might want to automate as much of this process as possible just to make sure you're achieving the highest levels of quality for your product. So as you can see, the most effective way to increase reliability beyond the limits of manufacturing is with testing. I'm excited to announce the launch of my pre-sale for these boards. So head over to nathanbuildsrobots.com to learn more. I'll leave a link in the description below. The first batch will be a special edition. They'll be gold-plated and hand-built by me. I'd like to give a huge thanks to PCBWay and Altium for providing their services for me to use. It's been really helpful, and I think it's really one of the best workflows, so you can produce really high-quality electrical designs.